relation. So how many parts of this solution it has? Hello. So how many parts of this one? This one has two parts, namely one is the solution to the associated homogeneous part, that is denoted by A and H, and other one is the particular solution, that is A and P. And whenever you are adding these two, you are getting the general solution to the non-homogeneous recurrence relation. Then, as I already have said, in order to find the particular solution, there are certain tricks. What are the tricks? So now this f of n, this special function, it can be either a polynomial, or it can be a power function, or it can be the combination of both. So let us consider that special function I am writing as b1 n to the power of t plus b2 n to the power of t t minus of 1 plus b3 into t to the power of n to the power of t minus of 2 plus so on so forth. And finally, let us consider we are writing bt into n to the power of 1 multiplied by s to the power of n. As already I have said, either it is a polynomial, or it is a power function, or it is a combination of both. That's why in general I have taken these two. A power function, that is s to the power of n, multiplied by a polynomial whose degree is t. N to the power of t started with n to the power of t to n to the power of 0. So it's a polynomial of degree t. So I have just taken, in general, I have taken as a product of two things. One is a power function, that is s to the power of n, and another one is a polynomial. Okay. So then, what are the tricks or what are the rules for finding? So the rule one is, if s is not a root of the characteristic equation. So whenever s is not a root of the characteristic equation, where you are getting characteristic equation? For the associated homogeneous part. If s is not a root, then the particular solution is A and P. That will be C1, or better I am writing alpha 1 n to the power of t plus alpha 2 n to the power of t minus of 1 plus so on so forth, alpha t n to the power of 0 is 1. So I am just writing that one into s to the power of n. So what this alpha 1, alpha 2, so on so forth alpha t represents? So they are simply whatever b1, b2, b3, so on so forth bt was, they are arbitrary constant. So simply those arbitrary constants are being changed and the polynomial remains the same degree, multiplied by the power function whenever s is not a root to the characteristic equation. Am I clear? Then let us consider second case, that is rule 2, when s is a root of the characteristic equation with multiplicity is m, with multiplicity is m. That means this s is a root of the characteristic equation, but how many times it has repeated? M number of times. Then the particular solution A and P is of this form. So first, the polynomial with change in coefficients, that is alpha 1 n to the power of t plus alpha 2 n to the power of t minus of 1 plus so on and so forth, alpha t multiplied by the same power function. Then what to be changed? Only a only a factor to be multiplied with this, that is n to the power of m. So why this n to the power of m is multiplied? Because s is a root of certain multiplicity, and that multiplicity is nothing but m. So that the particular solution is of the form, is of the polynomial of same degree having change in coefficients, so that from b1 b2 we have changed that one alpha 1 alpha 2 so on so forth alpha t. Then the same power function, that is s to the power of n, then we are simply, as this s is a root having multiplicity is m, that's why you are multiplying an additional factor, that is n to the power of m. Okay. So next, let us consider the other rule, that is rule 3. Let us consider we are getting s is not a root. First condition is s is not a root, and we are getting a polynomial of certain degree. So that as certain degree, so we must try to find the degree, the coefficients, value for the coefficients, namely alpha 1, alpha 2, so on and so forth alpha t. How we can find it? Such s is not a root. So a and p, firstly, we will get a polynomial, then multiplied by the same power function. Then we will just try to find the values for alpha 1, beta 1, b1, b2, b3, so on and so forth bt. How we are getting that, I will show by means of a example or by means of a question. So let us consider a question in this regard. So let us consider the question is given to be an, that is equal to 3 an minus of 1 plus 2n. So this one is our given question. Can you say? So this question, whatever I have taken, an, that is equal to 3 an minus of 1 plus 2n. So certainly this recurrence relation is linear or not? Yes, it is linear. Linear means its degree is 1. So what is the order? Order is also 1. Is it homogeneous? Not at all. So what this one is? Non-homogeneous type. Why? Because the special function is 2n. So here f of n is equal to 2n. Okay. So in order to find or in order to solve this one, this recurrence relation, first of all, we must try to find the solution to the associated homogeneous part. So what is the associated homogeneous part? The associated homogeneous part is an, that is equal to an equal to 3 an minus of 1. Okay. So what will be the characteristic equation? Who can say? So the characteristic equation will be r minus of 3 equal to 0. Okay. So what will be the characteristic root? R will be equal to 3. Okay. Then as you have got here r equal to 3. So what will be the solution to the associated homogeneous part? What will be your an upper one in h? What will be this one? So the solution will be simply some arbitrary constant, namely alpha, multiplied by 3 to the power of n. Okay, because previously we have got it. And here also this condition is given, A1 is given to be 3. So as you are getting ANH is equal to alpha multiplied by 3 to the power of n. Am I clear? Then in order to find for the second part, means solution for the non-homogeneous part. You see, what is f of n? Just compare the three rules. What is f of n? It's a polynomial. 2n means a polynomial. What is its degree? 1. So that what will be the particular solution or predicted particular solution? It will be a polynomial of degree 1. So I am writing this is equal to C into n plus d. So what is C? What is C then? C is nothing but an arbitrary constant. What is the d? Another arbitrary constant. Okay. If I am putting these values, as this is a particular solution, so putting this value in the set are the given non-homogeneous recurrence relation and equating the coefficient of equal powers of n. We can able to find the value of C. We can able to find the value of D. Putting that one, we can able to get the particular solution. Okay. So if I am writing here, what is the value of an? An equal to Cn plus D. That is equal to 3 multiplied by an minus of 1. So in place of an minus of 1, how much I should write? C into n minus of 1 plus D, then plus 2n. Okay. So in place of an minus of 1, again I am repeating, in place of an as the predicted solution, as here f of n is a polynomial simply, no power function is multiplied. So what will be its particular solution? It will take the form of a linear polynomial. So linear polynomial means a polynomial of degree 1. So the general linear polynomial form is C into n plus d. So that if I am putting that one in the equation, what I am getting? In place of an, I am putting here Cn plus d. That is equal to 3 multiplied by, what will be the value of an minus of 1? That will be C into n minus of 1 plus d. Then plus 2n. 2n is there. So now try to simplify this one. So I am getting here Cn plus d equal to 3Cn minus 3C plus 3D plus 2n. Okay. So now I am equating the coefficient of n or n to the power of 1. How much I am getting? C minus of 3C minus of 2 multiplied by n, then plus d, then minus of 3d plus 3c equal to 0. If I am equating the equal powers of n, coefficient of equal powers of n, so can I write here minus of 2c minus of 2 equal to 0? And if I am taking the coefficient of n to the power of 0, so I am getting minus of 2d plus 3c equal to 0. So solving the first equation, I am getting here c equal to minus of 1, and that putting that value here in the second one, we are getting the value of d to be minus of 3 by 2. So the value of c we are getting to be minus 1. The value of d we are getting to be minus of 3 by t. So what is the value of a and p? So I am getting here minus of n minus of 3 by 2, because cn plus d, the value of c is minus 1 and the value of d is minus 3 by 2. So I am putting that one, I am getting. So what is your general solution? Your general solution is an, that happens to be your ANH plus ANP. How much you are getting here? We have got here, how much you have got here? Alpha into 3 to the power of n, because ANH already you have got the value, and now you have got the value of ANP, or the particular solution we have got, that is minus of n minus of 3 by 2. Okay. So after getting this one, you can say whatever the solution you have got, it is not A, it is one of a general solution. But sometimes question asks, find all solutions. So we have got, namely, we have got two solutions here. One is ANH, that is solution to the associated homogeneous part. Another solution you have got ANP, the solution to the, or betterly I can say the particular solution. And then, as this is a solution which covers or which includes an arbitrary constant, alpha is there, so it is again a general solution. But as the question sometimes asks, find all solutions. So what is the meaning of find all solutions? All solution means here one of the initial condition is given that you have to check always. Here what is given? A1 is given to be 3. As A1 is given to be 3, using this initial condition, we can able to find the more defined solution. Refined solution means the arbitrary constant alpha, whatever we have already used for finding the solution of A and H. The value of alpha can be found out. How? If I am taking n equal to 1, I am getting here A1, that happens to be your 3. So that is equal to alpha into 3 to the power of 1 minus 1 minus 3 by 2. So if simplifying, what is the value of alpha? So alpha will be 4 plus 3 by 2 divided by 3. So that you can get 11 by 6. So that is 3 plus 1 plus 3 by 2. So that is 4 plus 3 by 2. So that is 11 by 2 divided by 3. So that you are getting 11 by 6. So you have got the value of alpha is 11 by 6. So the last result is AN. That happens to be 11 by 6 into 3 to the power of n minus of n minus of 3 by 2. This happens to be the more purified and more particular solution to the given recurrence relation an equal to 3 an minus of 1 plus 2n, where the initial condition is given to be a1 equal to 3. Okay. So let us consider another. Am I clear of this one? I'll send this one, don't worry. The same question now I have done. I'll send this one by tomorrow. The previous one also, these problems. Okay. Let us consider the another one question that is given to be an, which is equal to 5 an minus of 1 minus 6 an minus of 2 plus 7 to the power of n. where the initial condition is given. Okay, no initial condition is given in the question. So just see, this is a non-homogeneous type or not? Certainly this is a non-homogeneous type because the special function is f of n is your 7 to the power of n, which is a power function. Okay. And what are the other part of this one? The associated homogeneous part. So what are the associated homogeneous part? Associated homogeneous part is an, that happens to be 5, an minus of 1, minus of 6, an minus of 2. This one is your associated homogeneous part. Okay. So first of all, we must try to find the solution to this one. What is the solution? What is the characteristic equation? The characteristic equation is r square minus of 5r plus 6 equal to 0. What are the characteristic roots? r1 into 3 and r2 will be equal to 2. Okay. So what is the general solution to the associated part? So that is your ANH. So that will be alpha 1 into 3 to the power of n plus alpha 2 into 2 to the power of n. Because these techniques last time we have just discussed. So this one is your ANH. And in order to find what is your f of n here, f of n is your 7 to the power of n. So what type of function this one is? It's a power function. Such it is a power function by rule. What is the polynomial here? The polynomial is of degree n. Okay, the polynomial associated with this one is degree n. So you have to check here whether 7 is a root to the associated homogeneous part or not. Your answer is no, because one of a root is 3, other root is 2. So it is not a root of that one. So what will be your particular solution? By the rule A and P. That will be some arbitrary constant C into 7 to the power of n. What is C? The arbitrary constant. So now if we are just putting this in the given non-homogeneous recurrence relation, we can able to find the solution. What this one? The non-homogeneous recurrence relation is given to be an, that is 5 an minus of 1 minus of 6 an minus of 2 plus 7 to the power of n. So what is an? That happens to be your C into 7 to the power of n. That happens to be 5. What is the value of an minus of 1? What will be the value of an minus of 1? C into 7 to the power of n minus of 1. Because for an, you have taken C into 7 to the power of n. What will be the value of an minus of 1? C into 7 to the power of n minus of 1 minus of 6 into C into 7 to the power of n minus of 2 plus 7 to the power of n. I have simply substituted the values in accordance with the script, nothing else. Then go for a simplification. Whatever the value we are getting here, so see, whatever the common factor you are getting, here whatever the common factor you are getting, 7 to the power of n minus of 2 is your common factor, whether you are getting the common factor or not. 7 to the power of n minus of 2. So I can write here C multiplied by 7 square into 7 to the power of n minus of 2 is equal to 5 into c into 7 into 7 to the power of n minus of 2 minus 6 into c into 7 to the power of n minus of 2 plus 7 square into 7 to the power of n minus of 2. So from both these sides, can we cancel 7 to the power of n minus of 2 or not? So finally, how much you are getting here? 49c is equal to 35c minus c also minus of 6c then plus 49. So if we are simplifying them, what is the value we are getting? So 35. So we are getting here 49c is equal to 29c plus 49. That implies we are getting the value of c to be 49 by 20. So as you are getting the value of c, now we can replace that one in place of a and p. So that is, what is the value of a and p? A and p equal to c means 49 by 20 into 7 to the power of n. So what will be the general solution then? The general solution is an, that happens to be ANH plus ANP. So that happens to be your, how much you have got for ANH? Alpha 1, 3 to the power of n plus alpha 2, 2 to the power of n plus 49 by 20 into 7 to the power of n. So this happens to be the general solution. So why I am saying this one is your general solution? Because it contains two arbitrary constants, namely alpha 1 and alpha 2. So if two more initial conditions are given to us, we can able to find the value of alpha 1 and the value of alpha 2. So this solution becomes more purified. So here, for that reason, as no initial condition is given, that's why we are getting the general solution. Okay, we cannot able to get the most purified solution or most particular values for the said recurrence relation. Okay. So many examples in this regard, or so many questions in this regard, we can able to get and we can able to solve it. That doesn't matter, but more often or morely, you have to think of what are the three rules that that is stated. So rule 1, that is a polynomial fn, that is nothing, a polynomial multiplied by a power function. And what are the three rules are imposed? Try to follow that one. We can able to get it. We can able to get the general solution as well as the particular solution more quickly and more easily. Okay. Apart from this one, we have also some other special methods are there for solving recurrence relation. So before going to that one of a method is we can able to solve the recurrence relation by using generating functions. We can also, we are also getting different type of recurrence relation, and basing upon the type, we can also impose the appropriate method. What are they? So let us consider some special methods. So what are the special methods? Let us consider The first one, that is method of inspection. Method of inspection. So certainly you will find the recurrence relation must be given in the form of, it may be linear or it may be quadratic. You will find, but whatever the special function is supplied or whatever the special function is given, you will get a very big polynomial, or you will get, it may be in factorial form. So that whenever we want to solve this type of recurrence relation, first of all, our arbitrary method is, first of all, just try to, and it is also associated by some initial conditions. Maybe A0, A1 the value, or A2 the value may be given to us. So that employing or using those initial values and just taking for higher values, we can able to find the terms of that sequence. So after getting the terms or next terms of that particular sequence, by getting those terms, we can able to predict something. What can be the solution or what will be the form of the solutions? So whatever the prediction we are doing, that must be justified by the method of, one of a great method of proof, that is by induction. Okay. So whatever the steps, first of all, find step 1 is using initial values, find more terms of the sequence. Okay. What is step 2? Then whatever the terms you have got, predict some solution. As you have got in the previous one, I have said you have taken power solution is the predict solution of the recurrence relation. Likewise, you have to predict. So what may be the solution? Okay. That is by intuition. That is by certainly by your reasoning. And what is the third one? Whatever you have predicted, whether you have to give the justification. So justification of the solution. Whatever you have predicted, whether it is right or wrong, that you have to give the justification. And if your predict solution is justified by other terms or it is verified by other terms, then your answer or whatever the answer you have got, there your answer is right. Okay. So let us consider, I am taking one of a question in this regard. Am I clear? I have just taken here 3 steps. What are the 3 steps? First step is using initial conditions, using initial values. Whatever the initial values are given, try to find more terms of the same sequence. Okay. Let us consider the first term A0 is given. So using that one, we can able to find A1, we can able to find A2, we can able to find A3, so on and so forth, A4, A5, so on and so forth. So after finding that one, seeing the terms, we must observe some common feature in between the terms or common property by seeing these terms. So whatever the common property you are getting From that one, we can guess a solution. So whatever our guessing is, whether it is right or wrong, how we can justify? We have to take the method of proof. What is that method of proof? Induction. Method of proof is justification. For justification, the sufficient one, necessary and sufficient one is your induction. By using induction, we can justify whether the predict solution is right or wrong. Okay. So I'm taking a question that is also in your exercise. What is given? So that is E10. So this is given Bn is equal to Bn minus of 1 plus 4n cube minus 6n square plus 4n minus 1, where n is greater than or equal to 1 and b0 equal to 0. So the recurrence relation, whatever is given, that is linear. Yes or no? It is of non-homogeneous type. Because the special function is 4 f of n is your 4n cube. So this happens to be your f of n, the special function 4n cube minus 6n square plus 4n minus 1, where the initial value b0 is given to be 0. So what will be the value of b1? Try to put n equal to 1. So that is b0, the value is 0. Then whenever n is 1, how much you are getting? 4 minus of 6 plus 4 minus of 1. So how much you are getting? 8 minus of 7. So you are getting b1 is 1. If I am putting here b2, means the value of n is 2. So you are getting b1, the value is 1 plus 4 into 2 to the power of 3 is 8. 4 into 8 minus 6 into 4 plus 4 into 2 minus 1. How much you are getting? Try to simplify. 1 plus 32 minus 24 plus 8 minus 1. So how much you are getting? 32 plus 8 is 40. 40 minus 25 is 15. So this is coming to be 16. So B2 is 16. What is B3? So the B3 is 16. B2 means 16 plus 4 into n cube. So 3 to the power of 3 is 27 minus 6 into 3 to the power of 2 is 9 plus 4 into 3 minus 1, that happens to be 16 plus, so I think 4 and 27, 108 minus 54 plus 12 minus 1. So that is coming to be 120 minus 55. So that is 120 minus 55. So 65 plus 16, 81. So just see, your B0 is 0. B1 is 1. B2 is 16. B3 is 81. So can I write 16 to be 2 to the power of 4 or not? Can I write 81, that is 3 to the power of 4 or not? Can I write here 1 to the power of 4 or not? So from these 4 values, I'll just get a common property. What is the common property? The common property is the solution to this non-homogeneous recurrence relation is Bn. That happens to be taken in the form n to the power of 4. Okay. That happens to be n to the power of 4. But question arises whether I am right or wrong. How I can able to justify? Whether I am right or wrong. How I can able to justify? This happens to be the solution that I am predicting. That is my predicted solution. So I have to give a justification. How I can justify? I have to think for the induction. So, right, justification by induction. So here need not to go through the, as you know, in case of induction, it has two parts. What are the two parts? The first part is basis part, where the initial values to be tested. So that already you have tested. For 0 you have got, for 1 you have got, for 2 you have got, for 3 already you have got. So that what is your next part? In the induction probe, you have two parts. One is basic part or basis, that is known to be basis, and another one is induction part. So here the basis part is clear because all the initial values are already tested. So only the induction part or induction step to be tested. So what to be tested? Let us consider k less greater than, so 0 less than k is less than n. 0 less than or equal to k, this statement is true. That means bk equal to k to the power of 4. So you have to prove for for k plus of 1. That means we have to prove that bk plus of 1 is equal to k plus of 1 to the power of 4. That you have to show. Okay. So what is bk plus of 1? By this rule. From the question, from the given recurrence relation, non-homogeneous recurrence relation, we have got bk plus of 1 is equal to bk plus how much? 4 into k plus of 1 to the power of 3 minus 6 into k plus of 1 square plus 4 into k plus of 1 then minus 1. So what is the value of bk? Bk is nothing but k plus of 1, sorry, k to the power of 4. Because in the assumption you have taken. Then plus, you just go through simplifying, 4 into k plus of 1's cube. What is k plus of 1's cube? K cube plus 3k square plus 3k plus 1 minus 6 into k plus of 1 square, that is k square plus 2k plus 1 plus 4k plus 4 minus 1. So if I simplify, I am getting here k to the power of 4 plus 4 k cube Then here you are getting 12k square minus 6k square. So plus 6k square. Then you are getting 12k minus 12k plus 4k. So that you are getting 4k. Then here you are getting 4 plus 4. You are getting plus 4 is 8. You are getting 7 minus 7 minus 6 minus 1 minus 7. So that is plus 1. So you are getting here k plus of 1 to the power of 4. So by induction, it is justified. That means this is our predict solution is the original solution to this one. And for this one is your solution. Am I clear? So 3 steps that I have just written. Try to follow these steps. You can get through it. Okay. And another one, the other special method is your telescopic sum and telescopic sum as well as telescopic product. Then question arises where you are applying this telescopic sum and telescopic product method. Means you are getting a question of this type. How we can say that I must apply here telescopic sum here, I must apply here telescopic product here. So whenever I am writing these two conditions where to apply, when a recurrence relation is of linear type, first of all, and some, and more particularly linear type and order is 1. As I am writing linear, that's why I am not writing degree. Order is 1 means only a n minus of term is present. And special function, that is f of n, is added to it. Simply special function is added to it. So then at that extent we can apply. Then apply telescopic sum. Then where we can apply telescopic product? So when recurrence relation is linear, order is 1, okay, order is 1, and the previously described terms is in multiplied with the previously described terms. There you are applying telescopic product. Then apply telescopic product. Okay. So I am just giving you some examples in this regard. So you can just see I am writing here an is equal to an minus of 1 plus f n minus of 2 into f n minus of, sorry, n plus of 1. This is one of a book question that I have taken. So see, what I have written, which form is applicable here? Telescopic sum is applicable. Why? It is linear in nature. First of all, again, as my first condition I have written here, order is 1, and whatever the special function is written, that is a product of two certain type of function which has got some importance. What is that? The Fibonacci terms in the Fibonacci sequence. So here, if I am taking this an minus of 2, sorry, an minus of 1, I can get here fn minus n plus of 2 into fn plus of 1. So what is the value of fn minus of 2? What this value? This one's value is known to us. What this one is? So that is fn plus of 1 plus f of n. Then what is the value of fn plus of 1? Sorry, this is fn minus of 1 is given. Fn plus of 2 into fn minus of 1. So what is the value of fn minus of 1? Can I write this one is fn plus of 1 minus of f of n or not? So if you're just making, are you getting here right hand side? Are you getting here fn plus of 1 square minus f of n square? So here in the left hand side you have got an minus of 1. So now whatever the expression you have got, that have got simplified, and now it is in the form. So just try to put the values of n starting from 0 or whatever the initial value is given. Finally, we can just cancel all these terms in the left hand side. Finally, you will get a term an that happens to be a0 plus the right hand terms. Whatever you are getting, those are nothing but the standard values using which are just applying some mathematical forms or concepts. We can able to find the general solution. Am I clear? Just a minute. Okay. So some more questions in this regard is given, but the more common application of this one is finding sum of n terms, or finding sum of that is written to be sigma n1. So it represents sum of n consecutive terms starting with 1. Sigma n power t means sum of n terms that is in square form, and so on and so forth. We can able to find by applying this concept. How? If I'm just trying to find the sum of n terms, that means 1 plus 2 plus 3 plus so on and so forth. Or if I'm just trying to find the sum of square of n term. That means 1 square plus 2 square plus 3 square plus so on so forth. How we can able to get here? As you know here, k plus of 1 cube minus of k cube is how much? This is simply equivalent to 3k square plus 3k plus 1. Are you getting this one or not? So now, if I am putting the values of k in constantly, I can able to get the values or not. So if I am putting here, let us consider k is 1. So you are getting here 2 to the power of 3 minus of 1 to the power of 3. Okay. That happens to be 3 into 1 square plus 3 into 1 plus 1. Next, if I am putting here n equal to 2. So how much I am getting here? 3 to the power of 3 minus 2 to the power of 3. That happens to be 3 into 2 square plus 3 into 2 plus 1. If I am proceeding in this next, if I am putting n equal to 3, I am getting 4 to the power of 3 minus 3 to the power of 3 is equal to 3 into 3 to the power of square plus 3 into 3 plus 1. If I am just proceeding in this way, finally, how much I must get here? K plus of 1 cube. Finally, if I am increasing, minus of k cube, we are getting suddenly that is equal to this formula 3k square plus 3 into k plus 1. If I am just adding them all, you see in the left hand side, 2q, this 2q, 3q, or this 3q, all are will be cancelled. So whatever remaining then, k plus of 1's cube minus 1's cube is equal to 3 into 1 square plus 2 square so on so forth plus k square plus 3 into 1 plus 2 so on so forth up to k plus 1 has been added k number of times. So this is simply k. So that as this value we can able to find and this value is known to us. So I can just write here 3 into summation of I square. I starts from 1 to k plus 3 into k into k plus of 1 by 2 plus k. After simplifying, can I able to get the value or not? Then you can get. Okay. So this is all about today. Any doubt in this regard? Hello.
Hello, sir.
Yes.
Sir, I require your notes.
Because I have to go through your study material first.
Yes, sir.
Some questions may be there. So what I am giving, along with that, by tomorrow you will get the study material. Sorry, tomorrow you must get that one. Because I have not today, actually I have not gone through your study material, whatever given in this regard. So by tomorrow you will get there. So for that reason, you just send your name and enrollment number to our staff Bijay Babu,
Yes, sir.
and he will send it
Sir, thank you,
to
sir.
you. Okay, all of
Okay.
you should send that one. So by tomorrow 1 o'clock you will get all these things, because tonight I will go through these things.
Thank you, sir.
I'll just see whatever the problems are given in your book, whether you can able to get through it or not. Then I must do that one. Then I will send you.
Okay,
Okay.
sir. Thank you, sir.
So any doubt in this first page? I think simply you have heard these things, you cannot able to know. So please go through your study material, because from the study study material you are getting questions. Okay. So try to go through this one. I think I have just given some extra things that is not given in your study materials, because the three rules whatever I have given, that is not given, because most of the times you are getting short question from these three rules. Okay. So I'll just send all these things. Don't worry, by tomorrow. Any others? Any question from all, from any others? No. Okay, thank you.
Sir, Roach sir.